In this lesson, we're going to introduce the concept of angular momentum, and specifically the angular momentum of a point particle. Now, this concept of angular momentum we will extend into understanding the angular momentum of spheres and disks, rods, other objects that are rotating, but we're going to start by looking at just the angular momentum of a point particle. And we're going to really begin by looking at our definition of momentum of linear momentum. So we know that P, linear momentum, by definition, three equal signs equals mass times velocity. So that we already know. And the system we're looking at for right now is a point particle moving in a circle. And for us right now, we're going to say it's moving at constant speed v, just traveling in a circle. Now, the linear momentum of the particle is given by its mass times its velocity, and the only velocity we have is v tan when the object is moving at a uniform speed in a circle consistently. So there's our m, there's our v tan, there's our linear momentum. Well, we're now going to look at how can we also get this same motion in terms of our rotational variables and speak of the momentum as an angular momentum. Because when we convert to our rotational variables, that is the momentum that we are going to speak of. Well, we're going to do it in a very similar way. We are going to let the angular momentum, L, by definition, equal I times omega, where, notice, and please get this into your notes, conceptually, there is no difference. Check, right? We have the inertia times velocity equals momentum, and we have rotational inertia times velocity equals angular momentum. Now, the moment of inertia for a point particle, as we have seen, is equal to mr squared, and that we just have to have memorized. We do not want to ever have to think about what's the moment of inertia of a particle. It is mr squared for a point particle. So when we substitute in mr squared for I, and we substitute in v on r, remember v equals omega r, so omega equals v on r, we get some nice cancellation here. We lose one of the r's on top, we lose the r on the bottom, and we get mrv, or m, or r, mv. So notice that we get p. So linear momentum is now appearing as part of our angular momentum quantity. But we've seen that with v equals omega r. We have our linear velocity appearing in an equation where we're calculating the angular velocity. So it's really just a new perspective. Now, in terms of what we have, we can always multiply any equation by 1. So I could take this equation and just multiply it by 1, but let's think of, instead of 1, sine of 90 degrees. Sine of 90 degrees equals 1, and that 90 degrees in this problem specifically we want to think of as the angle between the r vector and the v vector as drawn from a common origin. Because in general, for the problems we are solving, we will not always have v only tangentially. There will have components. Some of the v will be in the tangential direction, some of it will be in the radial direction, but none of the v in the radial direction will contribute to our angular momentum, because no radial velocity is going to contribute to motion around the circle. So it does make sense. And the theta that we're going to use then, and we're going to let the cross product do this for us, just like we did with torque. It's going to pick off the v tan that we need by looking at the angle theta between r and v as drawn from the common origin. So therefore, in general, we get our cross product. Cross product is doing all the real heavy lifting for us. It automatically is going to pick out the VTAN that we need, multiply it by r to get our angular momentum quantity that we want. And please make sure you get this into your notes, that the point particle calculation will only and always use r cross p, and we will sometimes and actually often put in mv right away for p to do our calculations. However, if we are looking at a disk, a sphere, a solid object, we will always use I omega. We will not use r cross p for that calculation. Our units for angular momentum do not have a value specifically to themselves, just like linear momentum did not. R is in meters, P is in kilograms, meters per second. So our units for angular momentum is going to be kilograms meters squared per second. So just like we talked about momentum units, we'll be talking about angular momentum, really in terms of just an angular momentum unit without always going kilograms meters squared per second. But we do have to, of course, be consistent. So we'll be doing a lot more with angular momentum for the rest of this unit, and we'll also be talking about the angular momentum of disks and spheres as well.